Yes,
Hmm?
but you can start the presentation possibly tomorrow.
Oh, you guys are not ready to present?
Okay, there's one group ready to, there's some presentations ready.
Okay. Which one?
Yeah, for one of the stabs, then also Chebyshev.
Okay, so those are still under impedance matching on group one, so there's no problem with that.
Okay.
Whoever is ready can present to us. So we have that from group one, then group two will be passive microwave devices, group three active, group four Foster's reactance theorem and scattering parameters, and group five we'll be discussing these active devices. Group six, passive again. So it's six, so it's like about 7 per group. Safin, what did you say we are waiting for?
Just a minute, I set up my presentation.
Okay. So last time I realized that somebody had asked in the chat whether there are other applications apart from the microwave, the cavity resonators. There are several applications, whether you want to use them as amplifiers or just frequency sensors. And as you present, you will be able to see that even the klystron and the magnetron are used in different areas as microwave cavity devices. So for example, you can use it as a wave meter or a frequency sensor where if you have energy of a wave, you siphon it through that resonant cavity. And if the output reduces in amplitude, that means the energy has been absorbed within the resonator. when there's resonance to that frequency. So in that case, if the energy is dropped at the exit, then it means the energy is trapped within that cavity at the resonant frequency. So you'll be able to tell the frequency of that wave. So that's one of the applications. It can be a frequency sensor, so you should be able to explain. Can also be used as a filter in a microscope or in a klystron amplifier, which I'm sure one of the groups is going to present, or in the magnetron oscillator. Also, we'll see how you can use it, those cavities. So we agreed that the definition of a quality factor was about the ratio of the energy storage and the power that is lost. You may be asked to define quality factor in terms of LC circuits. Remember last time we considered that we are going to look at the quality factor for the cavity. So basically we defined energy as we wait for this group. Yes. So energy storage is both from the electric and magnetic field. So we may want to define the total energy. Is equal to WE plus WH, which you can write with time so these losses, the losses can be there, either the radiation losses, the electric dissipation, or resistance. So you can say that actually the energy within that cavity is reducing that much, or within an RLC circuit. So we are saying that the quality factor, so in this case, we define the quality factor at the skin depth, remember? My pen is not writing well. So we define this at the skin depth. So we can say this is the measure of the number of oscillations, the number of oscillations that the field would have before the energy which is stored reduces to e raised to -1 of its original value. So at what time do you think that happens? So you can say the quality factor is the measure of the number of oscillations that the field would have before the energy stored reduces to, before it reduces to E neg 1 of its original value. So at what time would that happen? So you differentiate the energy equation. So you'll have at T, that happens at T, is equal to 1 over to that, right? Because at that time, what will be the energy? W E to alpha, and T is 1 over to alpha. So this would be W naught E neg 1. So at T is equal to 1 over 2 alpha, you'd have the number of oscillations in radians will be actually just WT. So how many oscillations are there at that time? So the number of oscillations at that time when the value reduces to that in radians is omega t. So it means then now we can define the quality factor. So Q saying is the number of oscillations, so that will be over 2 alpha. And we know that the power dissipated is d omega t over dt. This will give us that dt is d omega t over pd. So it means we can replace it here. So Q would be over PD. So that's why we have that definition of Q. So Q is equal to omega WT over PD. And now we see why we normally say is equal to 2 pi times total energy stored over energy dissipated per cycle, because now this you can write as 2 pi, should be 2 pi f. So you can have 2 pi omega t over t times PD. And that would be 2 pi times total energy stored over energy dissipated per cycle, because now we have T times PD. Okay, Sefin, are you ready?
Yes.
All right, so just take note of that one, if just in case this derivation gives you a better understanding of the quality factor. Okay, then just take note of that. Otherwise, we don't concentrate on derivation, we use them as results for application. Okay, so I'll stop sharing, then you can go ahead.
We'll be presenting with Andrew Shabaki, so he'll be sharing the slides now.
Hello, is it clear?
Yes.
Let me try sharing using my laptop.
Okay, I'll start off. The Chebyshev transformer is adapted from the Chebyshev polynomials. Shabaki, could you please share your screen?
Yeah, okay. Hello, sorry for the confusion. So I was to take you through the first part. Yeah, so we're going to take you through the Chebyshev transformer, and yeah, Stephen and I will taking you the Chebyshev transformer. So to begin with, it was named after a Russian mathematician Pafnati Chebyshev, and is applied in areas of mathematics and engineering. There are two types of Chebyshev polynomials. The first kind and the second kind. Chebyshev polynomial of the second kind. Uh, Chebyshev transformers are designed from these Chebyshev polynomials. Next, Tony. So the Chebyshev polynomial of the first kind, um, it is denoted by Tnx, and it is within a range of -1 to 1, and it is Tnx cos n tan inverse of x, as shown there. And the Chebyshev polynomial can be defined recursively. So T0 x is 1, T1x is x, and as you can see on the slide, um, Tn1 plus x there at the bottom is equals to Tnx minus Tn minus 1x for n greater than 1. That is the Chebyshev polynomial of the second kind, and it is it is from these that T2, T3, and T4 can also be derived, noting that T0 is 1 and T1 is x, and when plotted we can see T1 is x and T2 as shown in the graph, where T2 is T is 2x squared minus 1. Yeah, next slide kindly. So properties of Chebyshev. You have orthogonality, roots and extrema, and in orthogonality, the Chebyshev polynomials are orthogonal with respect to the weight function, 1 over root of 1 minus x squared on the interval -1 to 1, and the roots of T and x are xk is equals to cos of 2k minus 1 n over 2n for k, value of k greater than 1, ranging from 1 to, yeah. The extreme of T and x occurs at cos of k pi over n for the range of k where k is from 0 to n. Chebyshev transformer design. The Chebyshev transformer is a multi-section transformer with each section being a quarter wavelength. The design of this transformer is done by equating the reflection coefficient to the Chebyshev polynomial, and the order of the Chebyshev polynomial is directly proportional to the number of sections in the transformer to be designed. The total desired reflection coefficient is obtained by obtaining the reflection coefficient at its junction by use of the Chebyshev polynomial. Consideration has to be given to the number of sections and the chosen reflection coefficient. Sefin, can you take it from here?
Okay, so for the design procedure for the Chebyshev transformer, we desire an equal ripple in the magnitude of the pass band. So to ensure that we'll need to use the trigonometric functions in the place of the previous x and 1 and the simple numbers in the previous part for the Chebyshev polynomials. So we'll now rewrite the Chebyshev polynomials in the form seen below, where the subject of where t is expressed in terms of secant and cosine, and it's each with the order 1 being secant of theta m and cosine of theta, all the way to the fourth polynomial, which will be used for a transformer with 4 sections. Then to be able to equate the reflection coefficient to the Chebyshev polynomials, we'll need to express the reflection coefficient as a being the amplitude of multiplied by the exponential of j, n being the number of sections that we require, then theta being our angle, then Tn secant of theta m cos theta is the Chebyshev polynomial that we'll use. So for a four section polynomial, we'll use T4 for our design. Please go to the next slide. So we have an example for a design. So design a 3-section Chebyshev transformer to match a 100 ohms to a 50 ohm line with M is equals to 0.05, and plot the reflection coefficient magnitude versus normalized frequency for exact designs using 1, 2, 3, and 4 sections. So we begin with noting that the number of sections we have are 3. Then we state the reflection coefficient so that we can begin, which in this case we'll be using the reflection coefficient is equated to the third polynomial because we are designing a 3-section transformer. Then in this case our A, which is our amplitude for the equation, will be equated to M, which is 0.05. Then to get the secant of theta M, we equate it to cosine, to the hyperbolic cosine, and we use the formula below. Then we make substitutions to get the angle theta M, and we have 44.7 degrees. Then after we made these substitutions, we now have to substitute it back into our equation. Now that we have theta, we can get the values of the reflection coefficient 0, the reflection coefficient not being the first reflection coefficient, then reflection coefficient not being the second one. And for this case, we'll start with those ones. Now, as we repeat it to get the reflection coefficient. So now we'll equate the cos 3 theta sine, which was in cos 3 theta, which was in the Chebyshev polynomial, to the term. Sorry, the cos 3 theta is in the reflection coefficient, then the secant cubed is in the polynomial, so we equate them to each other. Then using that, we can get the first reflection coefficient, which we have right here. Then for the second term, we equate the cosine theta to the second term of the polynomial. Then we have our reflection coefficient, the second one. Then using symmetry, we know that this the second coefficient and the first coefficient here will be equal to each other. Then the third coefficient and reflection coefficient not will be equal to each other. Then to now guess the characteristic impedance that we need for each section, we use this formula for n is equals to 0. Using n is equals to 0, we're using the reflection coefficient or the reflection coefficient naught and the impedance naught, which is the characteristic impedance given in the question. So then we get the natural log of the first characteristic impedance is equals to the natural log of the characteristic impedance plus 2 times the reflection coefficient naught. Then we have the first characteristic impedance. Then for the next section, we'll see this characteristic impedance in the next slide, which and then now here for this case, now for when n is equals to 1, we use the values of the first characteristic impedance, which you got in the question in n is equals to 0 above. Then we use the first reflection coefficient that we got earlier. Then we get the second characteristic impedance. Then for when n is equals to 2, this is now for the third section, we use the values that we've gotten above to substitute this. Then now in the next slide, we go to the plot of the reflection coefficient versus frequency for the multi-section transformers. So for this case, we see now the equal ripple that is within a specific frequency, such that beyond this place, the response doesn't obey what we expected it to do. And we now have our Chebyshev transformer. The next slide. Then the applications of these, both Chebyshev polynomials, they are used in approximation theory to minimize and maximize error, to minimize the maximum error in approximation. We also have Chebyshev filters, which are used in signal processing. We have numerical integration used in Gaussian quadrature methods. Then differential equations that are involved in spectral methods for solving differential equations. The next slide. And as a filter, the Chebyshev transformer is used to design filters, particularly bandpass filters, and the properties of the Chebyshev polynomial in the filter lead to the passband having equal ripples and the stop band having a steep roll-off. This is well illustrated in this image below. In this image here, you can see for the passband, the ripples are equal in magnitude. Then for any area as away from it, there's a steep roll-off. The next slide. Then for any further clarifications, you can check Microwave Engineering, fourth edition by David M. Poza. It goes into more details in chapter 5. Any questions?
Thank you, Safin, for the presentation from Group 1 there on Chebyshev transformer. Probably my people are floating because you didn't start from impedance matching so that they gather the theory, so that they see where the Chebyshev transformer fits in. But maybe they have something to ask or comment to give. What is the second presentation about?
And the quarter wave transformer.
Okay, you see, now you're starting from the top. I wish you started the quarter wave, but that's fine. So is there any comment to give to that group? You can also comment on how their presentation is. I liked the slide, looks very nice, and also the fact that you're using drawings always, and in the equations giving examples. That's a very good way of presenting. Any other comment from the class? Probably after I present the quarter wave transformer, maybe they will be more aligned and be able to ask or give comments. So we can proceed to the quarter wave transformer then.
Hey, good morning.
Good morning.
So my name is Clement. I will be using Samuel Sochor laptop to do the presentation on quarter wave transformer. So I will start the presentation. So for quarter wave transformer, mostly it is used to do impedance matching. So, and the reason as to why we need impedance matching is when the load is mismatched with the transmission line, and therefore we want to insert the QWT in between the transmission line and the load to prevent any wave from being reflected on the line. So I don't know why this. Okay. So I'll be using the code to do the rough work and then share the presenter later. So I will start. I hope you can see the whiteboard, everyone. Okay. So I will be presenting on the quarter wave transformer. And the reason as to why we use quarter wave transformer is to do impedance matching to avoid any wave from being reflected on the line. So basically, you can say the line that is being matched, say the transmission line or maybe a circuit from the source end, and then we have a load on the other end. So I'd say maybe we have a transmission line like that, like that. Let's say it has Z1, and then in between we insert quarter wave transformer to the load. Let's say this is our load ZL. And basically, the reasons why maybe you say it's a quarter wave transformer, it's because the length is a quarter wavelength of the wavelength of the frequency that is traveling on the line, or of the wave that is traveling on the line. And so if this, let's say this transmission line, we want to see the equivalent impedance of Z1 when we look at from this point here. And so if you remember the equation of calculating Z in generally, the general formula, we have so let's say this is Z naught. So referring to Z1 here, we will have ZL plus ZL plus Z naught plus J tan beta L divide by Z naught. Is it ZL plus JZL tan beta L. So we know beta is 2 pi over lambda. So BL will be 2 pi over lambda times the length. Our length is pi over 4. So our beta L will be pi over 2. Beta L will be pi over 2. So inserting that in the formula, now we will have ZL Z naught plus tan pi over 2 divided by Z naught plus J ZL tan pi over 2. So, and we know tan pi over 2 approaches infinity. So when tukiweka infinity kwa in our equation, so we'll have something like ZL infinity. So divide by infinity, infinity, here infinity, infinity. So we'll be having something like so of course J and J will go. These two values will be 0. Then we'll have Z naught squared divided by 1 by ZL. ZL. Yeah, so this Z naught is now our the characteristic impedance of the quarter wave transformer will be Z in ZL square root. So our Z in this case, we may consider it as a maybe the characteristic impedance of the line that we need to match. And then this ZL, you know, it's obviously the load impedance. So that is generally the formula of calculating the value of the impedance of the quarter wave transformer when you need to match it with the load to prevent any. This is maybe your transmission line on one end, the impedance of the transmission line on one end. Then you insert that your quarter wave transformer in the middle, and you'll have a line there. You'll have a line there. Let's say this is ZL. Then this is, in this case, maybe Z in, that will represent the transformer that is being matched, and then this will now be our Z naught. So basically we say we use quarter wave transformer to match the load with the any impedance looking from this side, either transmission line impedance or any other circuit from this end, to prevent any reflections in the wave. So maybe from that, anyone who has a question before I see if I have any other thing to add on.
Hello, Clement.
Yes.
So I had a question regarding the values of ZL that are compatible with matching
ZL, yeah.
PWT.
Yeah.
Any value of, can you use any real or reactive load for matching? Or
Okay, you can't match when you're using quarter wave transformer. You can't use it when you have the reactive part of it. So the first thing you have to do is you must do stub matching to remove the reactive part, and then after that you now use quarter wave transformer to match the. You can only use quarter wave transformer to match the real part at the resistive load. So if the load has reactive part, maybe that is capacitive or inductive, you must use stubs, either single stub matching or double stub matching to remove that part first, and then you only remain with only resistive part. Then after remaining with the resistive part, you use quarter wave transformer to match it.
thank you.
Okay. So any other question? Okay, maybe I can just arrive on the same formula, but using voltage reflection coefficient, but just the same. So you might find maybe some books will use this formula of finding Z in. So you can pick whatever you think can work for you. So, generally, maybe let's say at a quarter, we have E. I hope we remember this from our previous, it was electrodynamics, 8/4. So if you come up with that, get something like this, negative. Yeah. And so generally, your input impedance will be something like this. So Z0 1 plus 1 minus. So inserting that in your formula, you will have something like this: 1 minus L, 1 plus L. So generally, ZL is Z0 1 plus that 1 minus. So the relationship between this part here and this part will give you that expression. Looking it from the quarter wave section. So you can also derive that formula like that to get the same thing. So maybe the general statement I will make there is that if you have this circuit, so you can say the two impedances are matched by, let's say, interposing a QWT of characteristic impedance equal to the square root of the product of the two impedances between them. And as I said, the impedance can represent either circuits, transmission lines, or maybe the generator impedance. So any impedance from that side. So I don't know, I had slides, but I think it just covers the same thing I explained here. Let me see. So I think these are the slides. So as you can see, quarter wave transformer is a transmission line segment that is 1/4 of the wavelength long, used to match two different impedance in a transmission line. So okay, I think I was already saying this, so there's no need to repeat it again. Similar things. So maybe the applications part of it. Someone other question. Okay. So the application part of it, so it is matching two transmission lines with different characteristic impedances. Number two, matching an empty waveguide to a waveguide with the dielectric inside. Three, matching waveguides of different widths or heights. And then number four, matching dielectric medium. An example is microwave lens to free space. Then let's see the advantages. Simple to design, effective for narrowband applications. Limitations, frequency dependence, requires design and application, or maybe you can add another limitation concerning the question that Calvin asked. You can only use it to match resistive loads, and so if you have reactive loads, you will have to tune them using stub tuners. Yeah. Then I think that is it. Unless a personal, I think I'll be done. I'm done with that. So any question?
All right, thank you for the presentation. Let's have any question from class. Yeah, so your slides probably you needed to add some drawings on the slides, but you have presented very well when you are doing your class writing on the board. I don't know whether you looked at the notes that we have, the guiding notes from class, because we need to use those ones so that we know what it is that we need to cover. Or is it somebody else going to cover on there? Because we need to see the plot between the reflection coefficient that you're achieving, that is in the network, and where the quarter wave transformer is reducing that reflection coefficient in a graph or in a plot. Did you guys go through the class note?
Okay, we did, though we didn't have enough time to do everything.
Okay.
So even the presentations we did was just to guide us on what I was going to present. So if maybe we share the presentation, we'll include all of that, because we haven't so far done the stubs. The people who are supposed to do the stubs, so we haven't covered that yet.
But do you think if you go to that figure 1, you are able to explain what is happening or not yet on the class notes? Because we are concerned that we need to see how this is reducing the reflection coefficient, and then that's what we now look at and say, okay, the quarter wave transformer is band limited, and we need now to use the Chebyshev to increase that bandwidth. So we need to see the diagram and somebody to explain to us what it means. Anyone with class notes from that group? You should be able to get it. Just try to highlight you can present the PDF and then scroll down so that people see what you're talking about. that one. Do you think you can grapple with it, that figure 1, and explain what is happening there? Because it's a plot of a reflection coefficient against the angle. And then we have that rho m there. That is rho m. What is that? And we have delta theta at pi over 2. Do you think you are comfortable explaining that curve?
Can you kindly help me do that? I'm just having a look at it right now. So.
Okay. All right. Did we have any more presentation from that group that you are thinking you would present today? You are the first group, so don't worry. You're doing well. The other groups will do
No.
this.
We don't have.
Okay. Okay, so that was the start of the presentation, so don't worry. You have started very well. But next time, I'm sure, now we know that all of us, we need to be ready for class so that we start from, and that's why I gave you that PDF so that it guides you on where to start and what guides you into it. Okay. So, all right, so that's good enough. So what does Chebyshev transform achieve and how is it designed? That's a question on the chat there. Okay, so that's what the first group tried to explain, but I think it has not come out very clearly yet. It's supposed to expand that bandwidth that the quarter wave transformer just gives like a pulse. So you increase that bandwidth so that you are able to increase over large frequency bandwidth. You can lower the reflection coefficient. And from the diagram, it should be very, so they gave us an example where you have a 3-section. You could have a 2-section as I gave in the examples there. It's just to increase that bandwidth so that within that bandwidth, the frequencies applied, the reflection coefficient will be below that threshold, that rho m, because you need to operate where the reflections are limited. In this case, you can see that curve is changing for every pi. It repeats itself. So what I can do is let me just go through the PDF so that then you get the ground on the theory, and then probably you can proceed from there next time. But now we need to do the slides. Every group will present and do the slides, and then you share in a Google Drive for FEE551 2024. I'll give you the link when you think that you have given your all into those slides so that the other people in other groups will be able to read them. So I'll present the same PDF and we go through it. So these are some of the questions you ask yourself when you want to discuss impedance matching. What is it? What does it mean? Okay, and 2 main reasons why you would want to match the impedance when you're designing a microwave system. Okay, so those are the key issues from theory. And you explain further why impedance matching should be done for both the generator and the load to the line. Because you have 3 things. You have the generator, then you have the load on the other side, and in between is the line. Further, you may want to discuss why triple stub, double stub tuners are preferred instead of a single stub. I'm sure this one you guys will be able to present. And where the application areas, focuses where a transformer may be used in impedance matching. And then you are supposed to show for theta near beta L, theta, which is beta L near pi over 2, then the magnitude of the reflection coefficient can be approximated as given in question 26. That's a derivation you can do. Okay. Then you are supposed to plot, the main thing here is to plot the bandwidth characteristic of a single section quarter wave transformer. Okay, for a term wave in F field line. So that is the key there, so that you see why are we using that quarter wave transformer and how does it help us in reducing the reflection coefficient within that bandwidth. Then we have number 5 here, design the passband characteristics of a two-section Chebyshev transformer, and you're given Z over Z1 or Z0, which is 2. The maximum tolerable value of reflection coefficient is 0.05. It means in your design, even if it is the ripple characteristics, okay, so you do your designs and make sure that whatever you are obtaining is below rho m within that bandwidth, and then you will be able to see that the two-section Chebyshev transformer is able to widen that bandwidth bigger than what the quarter wave transformer would do. And then you plot the characteristics and see that. So I don't know why group 1 did not start here, because really this is where you just start explaining the theories. So from number 1 there, we know that when you connect a load to a generator, and I don't know who presented, who was using the Microsoft, but he did it very well. So you collect a node to a generator by, and when the wavelength is several meters, and the load and generator impedance are matched to the waveguide of the transmission line, you can use various transmission matching techniques to do that. So that's what we mean. We are now, what will really explain what it is why are we doing it? So we always have two main reasons: that we want to maximize the power that is transferred to the load. So matching the load to the source viewed from the output terminals allows for the load to receive maximum power. That also works for just power systems, but for us, the key thing in communication is the frequency sensitivity of the termination. So a small change in the operating frequency will actually change the electrical length, beta L, of a line by a large fraction of pi radians. You may think it's a small change because beta is actually 2 pi over lambda. That lambda is affected by the frequency. So if you multiply by the length, then you realize it's actually changing that a lot. And that then modifies the effective load impedance, which is at the generator end. And that again modifies the matching requirements. So actually the electrical length, if you interfere with that, which has frequency element in it, then it will be frequency sensitive, which then again, you can't communicate outside the center frequency, which will lead to interference. So this is really important in communication systems. So if you're asked to state any two main reasons why we do it for microwave systems, then it is important that you don't miss number 2, even if you were to miss number 1. But now that you're used to number 1, it means then you won't miss both of those two reasons. And again, why then do we have to match? We make sure that you match both the line to the generator and also the load to the line. That is more of, definitely, we need a perfect matching scheme. So it's more of the avoiding frequency sensitivity. Okay. So you match both to individually, match them to the line. And what is the reason for that? Okay, so when a matching network is used at the generator only, then there may occur a large standing wave field along the line if the original load is poorly mismatched. Now, standing wave here is like, okay, so because the input signal is coming in at the equal energy and reflected the same way, so you'll form a standing wave. There's a spelling mistake there, so we change is the maximum field strength which is required before the electric breakdown, because if there's a standing wave, a very energy concentrated wave, where you have a standing wave, and you keep on feeding that standing wave. So there's a lot of energy that increases. Now, the standing wave current also leads to greater transmission losses. Again, standing wave is highly energetic, so it will actually lead to more transmission losses. And again, you must use the presenting also on the stab matching, isn't it?
Yes.
Yeah. So just make sure you have some sketches so that we understand it easier. Just have some sketches for it. Then you qualify why a single stab you would need a double stab or a triple stab. And if you can find, areas where we apply that, it would be good for us. The application areas. So then from there.
Excuse me, sir. Can you kindly move to the previous slide? I think the page where we are talking about, I think it was a question. Yeah, this one. State and explain the two main reasons for impedance matching. Why impedance matching is desired in microwave system design. I can see the second answer that we have there is that reduces frequency of termination. And then I can see it is the most important one. I wanted to ask, why is it that we actually consider reducing phase sensitivity of the termination as opposed to minimization of the signal reflection that occurs in microwave system? Because the way I was thinking is that in practical microwave and radio frequency applications, systems like the radar system, the satellite communication, and even the cellular networks, most of them work with, they actually work well when there is minimized reflection of the signal. So my question is, how comes that becomes very important? Reducing the frequency sensitivity is very important than the signal reflection, the minimization of the signal reflection when it comes to impedance matching.
Who was asking that? I wasn't on the same page.
Davis.
Davis, probably I can't put a face to it. Okay, so Davis, when we say reduce frequency sensitivity, and we are talking about that small change in frequency, okay, will increase the electrical length, isn't it? What do you think is happening to that signal?
Pardon.
When we say that we are reducing the frequency sensitivity of the termination, that signal that has a shift in frequency, what do you think is happening to it? What physical phenomena is happening to a signal which has a shift in its center frequency? Because a signal can be absorbed, isn't it? It can be scattered, can be reflected, diffracted. So what do you think is happening? So it means it's just actually, you are right, that it is not only the reflections that we are concerned about for that signal. Whenever there's a frequency sensitive signal, it means some of them will interfere with another center frequency. Some of them will be split and will be scattered away from your signal path. Some will be reflected. So what we are saying, it is frequency sensitivity that is causing all that phenomena that makes you lose the signal. I don't know whether you get the difference.
Oh, I get it now.
Yes, so it's supportive of the fact that actually it leads to signal reflection, but not only reflection, even refraction, diffraction, and all that, and interference in other center frequencies. So the 2 points are just on the same thing. Is that okay?
Yes, it's okay.
Yeah. So when, yeah, I know in the second semester it will become clearer that, yeah, probably now you may think it's just about reflection, but later you realize actually the way the multipath modes are several. Some of them are even absorbed within a scattering phenomena like rain or, water, dust, cloud, and all that thing. Yeah. So for this case where we have a line, we are only talking about frequency sensitivity, but all those phenomena can happen where this signal is either reflected or diffracted or interfered with by another. So thank you for buttressing that point. So frequency, the signal reflection is just one of what happens when you have that sensitivity. Okay, any other comment or question? All right, so the group one will discuss this stab matching, microwave reactive element. So what you do here, make sure you just have some sketches from several references. I'm sure you should be able to get some sketches. So that's why I left them like this, so that the students can look for sketches, so that we see the difference between symmetrical diaphragm, asymmetrical one, and thin circular post, and all that. If you Google, you will be able to get those. We've got stab tuners as well. So long as you give her the sketches, then you'll be able to follow. Now, this has been discussed for the quarter wave transformer. Now I just need to go to the diagram so that you see the effect, the outcome of the whatever has been discussed. So reflection coefficient is defined normally. So you would see that this theta, when you plot, okay, you can have an equation on 32. You are asked to do, there's a derivation here for the reflection coefficient. Show that theta near bit, which is beta L near pi over 2. So that for that condition, then the magnitude of the reflection coefficient can be approximated by this. Okay. So we are saying near because you can see that equation 28, what happens when theta is near 90 degrees? Can somebody tell us what is the value of the reflection coefficient? Let's say theta is 90 degrees. What would be the value of rho?
Zero.
Yeah, it will be 0. So does it mean that that is really a desirable point to reach? Because we now need to choose this ZL and Z1 in a way, Z1 in a way that its value compared to ZL is such that we can achieve this equation 28 so that there's no reflection, because that's the desire. Okay. So we were deciding not to have any reflection for that signal. So in that case, then, if we can achieve this, then we know at a point where theta is 90, then the reflection coefficient will be 0. So when you plot that, then you realize plotting the reflection coefficient against the angle is what will bring us to this. We know that at pi over 2, it goes to 0. Okay, but it starts somewhere depending on the, the characteristic of that line. So it starts somewhere, then goes down to 0, then repeats itself. So you'd see after every pi that form will repeat itself. So we have a maximum up to pi over 2, then up to there pi, and then it comes down again, 3 over pi over 2. Again, it will go up like that. So it means we need to be able to communicate at certain frequencies where this reflection coefficient will be almost 0. So we can set our system such that the quarter wave transformer that you're using is able to give you a certain value of reflection coefficient. And for you to communicate effectively, you have a threshold. So you can say that for that system, the reflection coefficient that you should not exceed is rho m. So you set it somewhere, rho m. So at that point, if you set rho m, so you draw a horizontal line, the dotted line, so that you are able to see at what point does it cut these two curves where it's going down and up. Then it means within this, remember theta is beta L. So within that frequency, within that range of frequencies, you should be able to communicate without reflection or below that threshold of reflections. So that's why we are saying now that the bandwidth is d theta at that point. Okay. So within d theta, you should be able to communicate below rho m, which is the maximum threshold that you don't want to communicate beyond. That is the reflection, the maximum reflection coefficient that you don't want to exceed. So if you are able to tolerate that maximum value of the reflection coefficient, then communicating below it would be okay. And that corresponds to that d theta, which is very small looking at it. Okay, which is very small looking at it. So what do you do? Now the question comes, what is the remedy then? To be able to increase that bandwidth, because you want to communicate over, you know, a bigger range of frequency. So number one, what do you do to be able to increase that bandwidth? So group one, you can tell us what we know we can use a Chebyshev transformer to increase that bandwidth, but what else can you do if you only have quarter wave transformers? Did you come across anything? So you can use multiple sections of a quarter wave transformer to achieve the same, to increase that bandwidth. Now, how does then a Chebyshev transformer help to increase that bandwidth? So you can have another design where you have a Chebyshev transformer. In this one, you make sure that what you want to achieve is to have equal ripple characteristics, which make that coefficient, the reflection coefficient, to behave like a Chebyshev polynomial. And the Chebyshev polynomial is what we have in figure 2. That's the plot of the Chebyshev polynomial. Those are the values. So you see that you can use those to be able to design a system such that if you have the maximum reflection coefficient, okay, then having this Chebyshev polynomial helps you, depending on the degree, helps you to increase the bandwidth of that system such that you are able to communicate with at a threshold which is lower than rho m. So you can see from here, comparing the two, comparing these two, figure 1 and then figure 2 on the right, you will see now from at the point theta m beyond pi over 2, you're actually able to achieve equal ripple characteristics by designing that Chebyshev transformer. So in this case, you have actually expanded the bandwidth into which you can communicate. And now to the design of that, you define the reflection coefficient and their formulae, which helps you to calculate that bandwidth. Okay, so there are formulae that the group needs to take us through in their design that they are done. We need to see, you can add a drawing there so that we see the equations for this, how do you find this maximum reflection coefficient? How do you find it? From which formula do you find rho m in terms of z, l, and z naught, and some equation that gives us the polynomial? So if we are able to find rho m, that will help us to find the theta, the range of theta for which falls below rho m, and that involves some calculations. So we need to see those formulae. So you show us stepwise that after doing this, do this in your example that you gave. So you can also give another example in the passband characteristic for 2-section Chebyshev, which I think is in the notes here. If you can do that one, Again, design a passband characteristic for a two section, the one that given them. So you show us the formula that leads to, especially in the case where you've been given row M. So you are told don't go beyond this threshold, 0.05. So how do you find then? And you're given the ratios of the impedances. How do you get there? How do you calculate the fractional bandwidth? And then show us that plot that we are seeing here. So you can have a two section, show us the plot. You can have the three sections, show us the plot. And how do you calculate the impedances? Maybe Z1, Z2. How do you calculate the fractional bandwidth? How do you calculate theta M? You can see theta M in the diagram here. It's important for us to show how that is calculated from equations. Again, remember, as I said, in the fifth year, you use the results of the theory to try to do something that is practical. So you just need to show us those equations on what we normally call the polynomial coefficients. So we need to see that in a more logical way. I'm sure the class floated a bit on your presentation. And that, whatever I'm saying actually here, so you just need to, when it comes to the polynomial, I think that was good enough. The only issue is here now. For example, design the passband characteristics of a two-section Chebyshev transformer where you have ZL over Z1 is 2, and the maximum total value of the reflection coefficient rho M is 0.05. So you are supposed to compute the fractional bandwidth. You have reflection coefficient nominal, which is rho naught. Then we have rho 1. Then we have the impedances Z1, Z2, and then you plot the characteristics. So here, you can see already, actually, this should be ZL over Z naught, this one here, 2. So in that case, then you can have Z naught being 1 and ZL is 2. Theta definitely 0 in the past. Then this equation here. Okay. How do you use this equation here to compute theta M? How do you use this one to compute? Because if you already have rho M, so when you get theta M, because rho M is given, so you can see from this equation here, you can compute theta M. And now that you have theta M and rho M, you can compute rho 1. And then this is given. So using that, you're able to compute theta M. Then here we have the Tn. Why is this Tn important for us? What does it help us to compute? So from the formula here, like here in the notes here, I've not related why Tn is important, because there's a relationship between rho M and Tn. Okay, so you need to give us that relationship between rho M and Tn. Okay, because that's what helps us to get theta M. That's very important. Then fractional bandwidth, there's a formula, you can do that. Reflection coefficients, rho naught, rho 1, then the impedances, and then you plot. Okay. So you do that for the two section, you can do that for three section. You can change the value of rho M and see whether you get different factors. There are also approximations in some of the texts. So again, you can use those ones to give us a better presentation. So I'm thinking that group 1, tomorrow you present the stub matching. Do you think you'll be ready? Because if you'll not be ready to present the stub matching for the 1 hour, then I would rather you go back and do the presentation of quarter wave and Chebyshev transform again. Which one would be better presented tomorrow? Would you want to do a better job on the first presentation, or you want to go to stub matching? You still have up to next week. Stab matching, I would expect, as I said, several drawings. So if you didn't have them, so it means then tomorrow probably you will not be quite ready. You can make a decision on the go. What do you think? You think you're very ready to do the reactive element? Or the people who presented quarter wave and Chebyshev to give us more examples, more logical way of presentation. So I need to hear that. Any group leader who may talk for others?
Tomorrow we can do the stubs, the part that was remaining.
Mm-hmm.
Yes.
Okay. So then you prepare. But most importantly, this semester, we need to see diagrams. Eh? Without diagrams, it becomes quite... Okay, any objection to that? You think you want to go through this fast, or you just do the stubs? Because the stubs, I don't know, it's just 1 hour. I don't think we will finish them. You have a stub matching single stub, you have the shunt, the series, the diagrams, double stub and triple stub. You know, you can finish. Then the microwave reactive elements, just the shunt inductive. There's nothing much you just need to show us the diaphragms of the shunt inductive elements and the capacitive elements. Actually, you should be able to finish, especially if you just have the sketches and you're talking about them. Guided by, do we have anything here that can guide you? Yeah, there are. Yeah. So you just need to show us these diaphragms, how the orientation is. In the first place, on the shunt and series, yeah, that you just need to give us also a sketch on, you have a network of a load, and then you show us where you insert. If we talk about Z in is equal to 1 plus JX, so that normalized, how do you get the susceptance to remove that, the admittance or things like that? Yeah, so you should be able to finish if you just have diagrams to explain all this. And now, which other group will we be going to? Because we need to be logical. Next week on Tuesday. Will it be group 2? So that we start preparing them for their presentation next week. Active and passive. So which group is ready? The ones who will be presenting active or passive? Looks like they don't know their groups. Let me check here. Oh, I didn't save them on there. There should be some. So group 2 is dielectric terminators, attenuators, phase changers, directional coupler. Then the active is group 3. The tube devices, klystron, magnetron, TWT, oscillators. Okay, so group 3 or group 2 can present next week. What I'm asking, which one is ready? Group 2. So we go like that, isn't it? So we can start with the passive microwave devices. Is that okay, group 2? Are you ready? So here we can see also you need to draw. Then you tell us about the principal operation of that device and the areas of application. Very easy. For the dielectric current terminators, actuators, and that. But drawing very, very key. Group 2, you don't sound excited. Are you ready to present next week on Tuesday?
Yes, yeah.
Very good.
Next week.
Yes.
Okay, very good. So then so we are just trying to make you prepare for next week. Group 1, they've done very well. I like the slides there. The presentation on the Microsoft whiteboard was really great. Yeah, only that they started with the harder one on Chebyshev transformer. So I think guys floated a little bit. But let's let them. I'm sure they'll do a good job tomorrow on the stab matching. And then from there we learn how to present. But they have done very good, very well. Yeah, so that's how it is to teach. To be a graduate assistant, you start from where you have started. And teamwork. Actually, when a question is asked, even the other team members should be able to help the presenter to answer. It's not just the presenter to answer it. So are there more questions on what was done today? We can discuss that.
Yes, I have a question.
Yeah.
Yeah, so we looked at the Chebyshev transformer. Now I remember last academic year during electronics, we looked at other filters like Butterworth and Bessel. So I find myself naturally inclined to ask if we can have maybe now the Butterworth transformer and Bessel transformers, and what kind of applications, let's say for example you want to do some audio, you're working with audio, or maybe you're working with other kind of let's say the frequencies, what will be the best kind of situation that would require one to use, let's say, the Chebyshev in what kind of communication system?
So you want to apply that to low frequency electronics or high frequency? Because here, remember, when we started, we are saying that at high frequency, we prefer this kind of resonators rather than the RLC resonant circuits, isn't it? Okay.
Yes.
So the filters we use, we are confined by the frequencies which we want to apply. Okay. So it depends on the frequency of application and what is it, where do you want to apply it, in what kind of device. So that makes you make a decision and on what fundamentals to use. Okay, so here we are just learning the fundamentals and we are seeing various characteristics of different methods that have been brought forward in literature. We cannot discuss all of them. For us, it's just to look at the fundamental ones, the ones that use fundamental principles of physics. Then we use them, design a few application areas. If you want to do any other further application, then you now use the basic knowledge that you have, that actually for this kind of material, I cannot apply this frequency because of this. So it means we are not really very far from physics. So for us here, we look at the physics of it, whether it is on the material or in the design or the characteristics of so mainly most of the time is the characteristics of the materials that we use that define what frequencies we can actually apply. And then after that, using that fundamental, then you can now apply it anywhere in whatever thing that you're doing, whether it's just low frequency electronics or high frequency, and what kind of energy you want to deliver, what kind of, okay. power losses that you expect in that system. So for me, I don't want you to confine yourself in what application area is it that you want to do now. I think you get the problem that you want to solve. That is how we learn. So you get the problem that you want to solve, and then now look at the fundamentals. Is the fundamental we discuss now sufficient for you to make a decision in what to use? Okay. So I want you to have that philosophy rather than what is it in the text that has been discussed before as an application area. So we can't gather all of them. I can't tell you that I know all the application areas where all these things have been used. I don't know. I've not read. So the power we give is just ability to have the theory, to apply anywhere, but you know the limits. Why are we limited to use RLC in the low frequency and these resonators in high frequency? Okay, what are the constraints on those materials that we use there? There are also materials that cannot, probably they're highly conductive, but again, they could be very expensive, or their temperature rise is quicker in those frequencies. So those are the kind of things we need to learn, and wave propagation. So I would just give a general answer like that, you look at the application area, and then is it possible for you with what you have learned now to apply your knowledge and design a circuit that is appropriate for it? I don't know whether that answers you, or you may explain your question more further, then I see whether I have something more descriptive.
Yes, that answers me. And on Chebyshev, the ripples that come with it, is it a desirable effect or it's a trade-off that's acceptable? And what's the other characteristics that maybe we are trading off for the ripples?
For these ripples here, remember
Yes.
if you look at it properly, we are saying that the Chebyshev transformer is able to give us the ripples within the bandwidth that we desire, isn't it?
Yes.
So do you think it's a good thing or not? We are able to use it. It seems, go ahead.
I'd say it seems to be a consequence of what you're trying to achieve.
Oh, it's a consequence of what we want to achieve. Is it a consequence? Why do you think it's a consequence? Explain.
Because from the Chebyshev filters, the ripples are a characteristic that comes with the Chebyshev.
Exactly.
So I'd say it's not.
What we want to achieve is the consequence, isn't it?
Yes.
Yeah, what we want to achieve is the consequence. So that is good for us. That when we use a Chevy transformer, because it has this ripple effect, then it means it is going to cut off the peaks of the reflection coefficient, isn't it? And that's our desire. We want to desire where there's minimum reflection, isn't it? So for Chebyshev transformer, it's able to give us these lower peaks of the reflection coefficient for a wider bandwidth. So it means then it's opening up our communication system. So we are able to use under several frequencies. The same network we can use under a wider bandwidth of frequencies. So that's a good thing. So unless you're asking something else.
Yeah, it's just I remember from the discussions we were having on electronics, the Chebyshev, one of its good characteristics was it had a sharp roll-off, and one limitation or undesirable characteristic was the ripples. So
exactly, yeah.
I just wish.
Yeah, so you find it contradictory, yeah? That is true, because one of the things for electronics that it vanishes, it actually vanishes the peaks, isn't it? But in this case, we are actually applying it in a scenario where whatever it is ending up vanishing is good for us, isn't it?
Yes.
Yeah, so that is the only thing why it looks like the disadvantage the other side is actually an advantage this side, because now we are applying it in a system where the reflection coefficient is our outcome, and we would like to reduce it. So it means the vanishing behavior characteristic becomes a positive thing, isn't it?
Yes.
Yeah,
Yes.
yeah. So try to map this kind of two knowledge areas. Normally in engineering, definitely, as you are saying, we normally have a trade-off always. But you can use those trade-offs. You can see you can always use those trade-offs depending on the application that you want to apply it into. So in terms of reflection coefficient, it works for us. Yeah, so thank you for being very keen. That was who was asking the questions?
Samuel.
Someone. Okay. Yeah, thank you very much for giving us the insights there from electronics.
Yeah, thank you.
All right, so drawings, class, drawings, always sketches. Even if you go for engineering registration board, they will always ask you to give, where's the drawing, So let's always sketch, it's easier, even for our brains to always master when we sketch. Especially first semester, I normally find it quite abstract. And this is normally the best way to handle it when the students present, so that you don't just hear monotonously from me giving you characteristics of devices that you don't even see. Okay, so let's look forward to tomorrow's class and see group 1 give us the presentation of star matching. You can register your attendance on the chat with your registration numbers. We end there.